Hello everybody and welcome to my talk about routing of energy infrastructures, according to the motto, one rule to grow them all. What does that mean? Well, the idea came up while spending some time in New Zealand. That is why this work has been done in collaboration with my colleague Dr. Bart Görten, who is working at the Zoology Department of the University of Otago. So when I was there, I saw a paper about the neuronal branching of brain cells. So basically an idea how brain cells grow in an efficient way without having a final plan of how they should look like in the end. This kind of reminded me of planning energy infrastructures. Here it is often also not clear where the future consumers would be and who needs to be connected to a future grid, and therefore also the final topology for a thermal or maybe also a hydrogen network is not clear at all. So I had a closer look to maybe find an answer to the question, what is the best topology for an energy network? So if we look into network planning, many aspects play a role, of course. The site analysis, the load analysis, also consideration of redundancy measures, maybe scalability, of course, the integration of security measures, and of course also the evaluation of the costs for installation. But not all of these aspects are tackled by the following idea. But one aspect, the network structure, is most important, in particular for new networks. And the determination of the topology of an energy network will be in the focus of the next few minutes in this talk. Let's see how nature is growing networks and what scientists found out about branching a neuron. It all dates back to a guy named Ramon Cajal. He was one of the first who did research on observing and drawing brain cells. His research was so good that he got the Nobel Prize in 1906 for that. And from these famous drawings, he derived the idea that the topology of a brain cell follows a combination of just two rules when it comes to growing and branching. They do not have a final construction plan, but they grow step by step, optimizing their topology with each edge they build. The two rules are, first, minimizing the total amount of wiring, which will lead to a minimum amount of material, and second, minimize the path length from each point to the root. This leads to a minimal loss in the conduction. So the idea also implies that there's a starting point, a root, and that edges and nodes are involved, which leads to the concept of a graph. Looking into the very basic graph theory, we find that the first rule of Cajal fits the idea of a minimum spanning tree algorithm. This idea had been used for electricity grids over 100 years now. So the minimum spanning tree describes the idea of connecting all nodes of a weighted graph in a way that an addition of weights is as small as possible. Here you can see some examples of 30, 60 and 80 points that I generated. To show some effects, I added the idea of producing a random number of points which are based on different density distributions. So first, on the left side, we see an equally distributed amount of points. In the second or in the middle graph, we see a linear distribution. And in the third, on the right-hand side, we see a radial distribution density where I picked the points. Then I used very easy the implemented function in Network X package to get a minimum spanning tree. The second rule of Cajal's neuronal branching seems to be connected to the idea of the shortest path. In a weighted graph, you pick two nodes and look for the connection within the graph where the addition of weights is minimal. So far, so easy. But now let's add the idea of growing a graph. This leads us to the second part of this talk, describing the graph algorithm itself. Coming back to the paper I found by Kunz and colleagues. He used the two rules by Cajal to derive an algorithm, which is explained here. You can see here figure 2 out of this paper. The most important point is that we have a root, which is, for example, called number 1, or on the right-hand side is the black dot in the middle of this red cloud. Then we create a carrier points depending on, let's say, a density distribution of some parameter, which are shown here as red dots. Next, a greedy algorithm optimizes the two rules for the next point closest to the root and places an edge. Then we look at the newly connected node, and the greedy algorithm is looking for the next optimized node to connect to our graph. The greedy algorithm has a parameter which is called balancing factor, short BF. And as you might guess from this figure here, the BF is kind of a controller between more shortest path or more minimum spanning tree. First, let's understand the idea of adding a root to the two graph algorithms. Here you can see again 30 points and the application of the shortest path. This always leads to some kind of star. But what you can see is, depending on the chosen route, it looks different. So the choice of the route is also very important and therefore a parameter to choose. We have to keep this in mind. And the same is true for the minimum spanning tree algorithm, which looks different for a different choice of the root nodes. It is time to look into the cost function of the greedy algorithm. Here we have two parts, one part for each of the Cajal rules, the minimum spanning tree and the shortest path. They are connected by the balancing factor, BF. From the equation you can see that for a balancing factor of 0, the minimum spanning tree is dominating, while for a balancing factor of 1, we will get a star, which is the shortest connection between the root and each point. Keep also in mind that in the following, the weights of the edges are defined to be the distances between 2 points. Here you can see the algorithm in action. Starting at the root, which is here labeled to be 0, the algorithm starts with the closest point and connects it with an edge. Then it is testing all close by other points until the cost function finds a minimum. From the next node, the connection is searched again with leads to a minimum of the cost function. And so on. You can see the optimized graph in red on the right side. This can be done for several balancing factors, resulting in different graphs, which will always look like a minimum spanning tree or a star from the shortest path algorithm. This is a result for a balancing factor of 0. This is a result for the same points for a balancing factor of 0.7. And this is a result for a balancing factor close to 1. This is another example of different balancing factors. It is based on 50 randomly distributed carrier points within a 100 to 100 grid. The root is here labeled with 80 and is depicted by the green arrow on the right upper side of each panel. As a result, you see for a balancing factor of 0, it is close to a minimum spanning tree. For a balancing factor of 0.5, you already see some straighter connections to the root, while it is clear that we come close to a very straight connection between the root and each point when we go close to the balancing factor of 1. So I hope the idea of growing a graph is clear now. Then let's come to an application in the real world of energy networks. First, let's understand how the algorithm can grow a regional network. So for the first example, let's fly to New Zealand, to the beautiful but cold city of Dunedin on South Island. Contrary to other cities on North Island, it's getting quite cold in Dunedin, so space heating is definitely an issue. Therefore, Dunedin is one of the few cities which already have a small heating network, providing heat to a hospital and the university. And so let's assume they want to plan a new thermal heating network in another city district. To find a good new topology, we can use our new algorithm. Therefore, we first get a city graph from OSM, which is OpenStreetMap. From that, we extract the nodes, which we define to be the new heat consumers. And then we use first the minimum spanning tree algorithm, and second, our new neuronal branching algorithm with, let's say, a balancing factor of 0.5. So let's have a closer look on our results. This is a district of Dunedin together with a network topology. Now we can see if the topology fits with streets, or for example, if it is passing through properties. Based on this, maybe we get also already an idea on the differences between these two algorithms. And because I have chosen an implementation where you can just choose an address and plan a grid for basically every place in the world with OSM data, we can do the same trick with Cottbus as well. I have to admit this is right now more a kind of proof of concept thing, because there are already a lot of networks, including a heating network, present in Cottbus. And the algorithm is better used for new network topologies. But nevertheless, you can do the same thing again, like in Dunedin. You choose an address and get the city graph. From this, we generate new possible consumers for our network. And then we use the minimum spanning tree as a default to compare our results with, and then we calculate with our new neuronal branching algorithm with a balancing factor of 0.5 a new network topology for Cottbus. And to get a better impression where we did it, we can also see here the map of Cottbus together with the new topology. Good. So let's come to another, maybe more appropriate use case, which is based on creating a national network. So let's see if we can grow, for example, the new hydrogen network for Germany. So let's assume we talk about the new hydrogen network. What we need to do first is we have to pick a route, which could be, for example, a place or a source where the hydrogen comes from. This can be, for example, a harbor, like here in Brunsbüttel. Second, we need a density distribution to create our carrier points. In this case, I have chosen to take the population density of Germany. which is not totally correct. So maybe we should more use a forecasted hydrogen demand density. But for our small example here, let's start with the population density. Then from this density, we draw, let's say, 150 carrier points and calculate for these carrier points a graph with our neural branching algorithm with a balancing factor of 0.8. This can be done with different input parameters, as discussed earlier. For example, we can change the balancing factor. Here, for example, are 3 plots using the balancing factor of 0.6. Since with each run of the algorithm, we draw again 100 different points, the resulting network topology looks different. Another parameter is that we can change the number of points. We can, for example, change from 50 to 100 or 150. So this is also a parameter we have to keep in mind. With this algorithm, we can therefore generate a lot of new possible topologies. So question, how do we know which is the best topology for our future grid? So this is actually a good point. So let's go back to the paper of Kunz and colleagues and see what they did. I think actually they used some kind of trick. You can see here in the figure from their paper that they started with A, which is a real existing starburst amacrine cell. From this they derived a density distribution, which you can see in B, and then they used the algorithm to create C and D, so topologies with different balancing factors. From this resulting topologies, they calculated the total cable length, the mean cable length to the root, and number of branch points. And this they compared with the original real total cable length, mean cable length to the root, and number of branch points. And from this comparison, they got the perfect balancing factor. But the question is, can we do this with our energy grids as well? So we can compare what Kunz and colleagues did with what we did. So we started with a density distribution, which was the population density, and then generated different topologies for our future hydrogen network. But what could be the existing network? There is no hydrogen network present yet. If you have an idea, please let me know and put some ideas into the comments. So while waiting for your answers and your ideas in the comments, I'm going to present what we had in mind on this point. We see actually two different approaches here. First, a purely graph-based approach, and second, something I call engineering approach. So let's have a look. So graph comparison is fundamentally derived from the idea of graph isomorphism. So the question if two graphs can be considered structurally the same. Maybe this is not what you want in the end, but let's look into the basic idea. So we can globally compare the graphs. We can do this on a meso level with some substructures which appear, or we can do it on a very detailed local level. Of course, using this idea, we need to define what is a good graph for an energy grid, or what are good features for an energy grid, and what is something what we don't want. In more detail, under known node correspondence metrics such as delta-con, employ the Matsushita distance to assess connectivity, while cut-down distance considers the division of a graph into subpart structures. And on the other hand, Unknown node correspondence involves summarizing the global structure into statistics or distances, such as the graphlet correlation distance, which helps compare graphs without prior knowledge of node matching. Additionally, the meso-level measurements like zinc to source distance offer insights into the geometric mean of paths with the network. So, in the following, we will look into these new methods and metrics and see if this can help us to make the decision of which of our grown energy networks is the best for our use case. A second approach is something I call the engineering approach. This is a very simple basic idea that we take the resulting topologies of the graphs and build out of them real network elements, like power grids with Panda power, heat networks with Panda pipes, or hydrogen networks with Panda pipes. And from that, we get voltages and overloadings and pressures, mass flows and temperatures, and then we are able to compare the different topologies which come out of our algorithm. So this was the presentation on the status of our small project, where we try to use a neural branching algorithm to grow energy networks. If we come up with a scientific publication on this, I'll let you know. Until then, have fun with coding.